Welcome back to our series on mathematical statistics. I'm Mark Ledbetter. This is video 25. We are in lecture 11. This is part B of that lecture, and we are in part 3 of sufficient statistics. Last time we did the example of the normal distribution when we wanted to find the sufficient statistic for mu when we already knew the value of sigma. Now that's very unlikely in real life, but this is a simpler case and we could do it using the methods we've learned so far. But it's not surprising that the sufficient statistic for mu of the normal distribution is x bar. Okay. In fact, we saw that x bar is the sufficient statistic for the binomial parameter p and for the Poisson parameter lambda. So x bar is a very common sufficient statistic. So now that we have an idea, I hope, of what a sufficient statistic is, let's try to look at the concept, what it means a little bit more. So hopefully by now you're able to find a sufficient statistic using the factorization theorem. Okay? So this is called the sufficiency principle. So this is about the concept. This is the key point that you need to understand. So let's say that we call capital T a statistic, a sufficient statistic, and it's a function of the random variables from our random sample, so x1 to xn. So if this is a sufficient statistic for our parameter theta, then any inference about theta should depend on the sample only through t. Okay? So t should be sufficient enough for us to perform inference and to understand the sample. And we're going to call it t of x just to clarify that we're talking about x. Now, what we're saying here, or in other words, let's assume that we take two samples. And when we take two random samples, the first one we're going to call little x, and so that is x1 up to xn. These are actual value or points or values, observed values. Okay? And then W is going to be another random sample. And so these again are observed. Well, I can just draw the line to the other one, can't I? So these are also observed values. And so these we call two sample points or two samples. And let's say that we take these two random samples and then we calculate our sufficient statistic t based off of x, and we do the same thing with w, and let's assume that they're equal. Not the random sample. The random sample is going to be different because it's random, but let's say that we get the same value of our statistic when we do that, say the x bar it might be. Then the inference about theta should be the same whether we observe the sample x or whether we observe the sample w. So in other words, if both of these we calculated x bar equals 2/3 and we calculated that w bar equals 2/3, then we get the same result about the inference. Okay? So here is an alternate definition. This is the actual definition, and it's a lot more difficult to use than the factorization theorem. So our textbook wisely used the factorization theorem as the definition because, again, it's a lot easier to use. And I don't think that they put this in our textbook, but I wanted you to be exposed to this so that and see an example of how you use it. And so hopefully this will help you appreciate the factorization theorem, and you're going to have to know how to obtain a sufficient statistic using this definition. Again, it's a lot more involved. So let's take a look at this. A statistic, t of x, is a sufficient statistic for theta if the conditional distribution of the sample x given the value of t of x does not depend on theta. So the conditional distribution. So this goes back to us having to find the distribution of the test statistic. And that's the only way that you can determine using this if it's a sufficient statistic or not. So what we're saying is that the probability that x is equal to little x, given that the sufficient statistic is equal to some value t, that probability is independent of theta, so it does not contain theta in its expression. So let's look at this example 3. So we have a random sample from the Bernoulli distribution with a PMF, of course. F of x theta equals, or I shouldn't say theta, but theta here equals p. Okay, so I will correct that to say f of x p is equal to p to the x, 1 minus p to the 1 minus x. X can take the values 0 or 1. And of course, p can be in the range 0 to 1, including 0, including 1. First, we want to use the factorization theorem to show that the sum of the x's is a sufficient statistic for p. In other words, y equals the sum of xi is a sufficient statistic. Then we're going to use this alternate definition of a sufficient statistic to show that y is a sufficient statistic for p. Okay, so let's get started with this. First, so this is A. Recall that y equals x1 plus up to xn is a binomial distribution with parameters n and p. And we learned this last semester, and this is something you really need to know because a lot of the problems are just going to give you that it's, let's say in this case, just tell you Bernoulli. It didn't tell you that the sum was binomial. So that's something that you really need to know. So you need to know those transformations that we went over last semester. Okay, so the joint PMF of x1, x2, up to xn it's a random sample, so again, they're IID, independent and identically distributed, so they have the same exact PMF, and since they're independent, we can just multiply their PMFs to get the joint PMF. x1 up to xn, p is equal to the product I equals 1 to n of p to the xi, whoops, didn't write that very well, xi, 1 minus p to the 1 minus x sub I. And so when we do this, we're taking p to the x1, p to the x2, up to p to the xn equals p to the sum of xi. So that's equal to p to the sum of xi. Now, don't forget for this other one that you're doing a similar thing, but you have more to it. You have 1 minus p to the 1 minus x1, 1 minus p to the 1 minus x2. So you've got this 1 in front, so it gets treated the same way, so 1 minus x sub n. So if we're adding the exponents, we'll have 1 minus, x1 plus 1 minus x2 plus 1 minus xn. There's going to be n of these x's, so this is going to be 1 minus p to the n minus the sum of xi. Okay? So make sure that you know how to do these, the algebra here, so that you can get the right answer. All right. And so then we have, okay, so here is the function. Now, using the factorization theorem, we need phi of x, and that's the x sub 1, x sub 2. Actually, this is going to be phi of, I can just say, our sufficient statistic, so u of x1 up to xn, and p. And then we need h of just x1 up to xn. Well, both of these terms have p in them, our parameter. So where in the world is h? Well, h is going to be 1. So what we're going to do is, it's true that this is equal to 1 times p to the sum of xi and 1 minus p to the n minus sum of xi. And so this becomes h of x, 1 up to xn. And you say, how can that be? There's no x there. But we could say that it's xi to the 0. And so that would be 1. All right, so it can be written as a function of the xi's, okay? And then this has the sum of xi, which we're wanting to show as our sufficient statistic, and p. So this is going to be phi of sum of xi, p. Therefore, by the factorization theorem, sum of xi is a sufficient statistic for, you should always say what it's a sufficient statistic for p. All right, so that wasn't too hard. It's just tricky that you have to know that h is 1 in this case. Now, so for part B, notice that we are using t of x equals y. So here we said y is equal to sum of xi. We were using y for our sufficient statistic, so I should put that in there. Y equals sum of xi. Okay? Is a sufficient statistic for p. Notice that we are using t of x is equal to y. So t of little x equals little y. So what we need is we need the probability that y is equal to y. That makes this a little simpler than using t in there. And we know that y, so t of x is this, so y is equal to here. And so t of x is a binomial in p, because t of x and y are the same. So this, we use the PMF of the binomial n choose y, p to the y, 1 minus p to the n minus y. That's a lot easier to write than those sum of x's and everything, right? We're just using y for the sum of x. Okay? And y can take values 0, 1, up to n, and p is in the interval 0 to 1. So then, the probability that x is equal to x given t of x is equal to little y is the probability that x is equal to little x, and the comma means and here. Capital T of x equals little y. So that's by the definition of the conditional distribution, we have the probability of this and this divided by the probability of the given, the probability that T of x is equal to y. So when we look at the intersection here, we have we have the probability that x is equal to x, and that is equal to p 1 minus p to the so we have actually I've written this, we should have y here, sorry. Y is equal to y. And then this makes it a little easier to follow, I think. Y is equal to little y. No, we can't have that. We have to have x, I'm sorry. Yep. So we have to do the intersection. And so the probability that x is equal to little x, since x is a Bernoulli, this is going to be, but so this is going to be the probability of y 1 minus the probability of n minus y for, remember, x is a vector here. And then the probability that y is equal to little y is, since that's binomial, see, this is a vector but not a sum, not the sum. This is the joint PDF, right? So this is the joint PDF, and so we can write this as p to the y 1 minus p to the n minus y, okay? And this is a binomial, so it is, as we showed before, it is n, choose y, p to the y, 1 minus p to the n minus y. So we're looking for the intersection of these two things, and that is this quantity. It's in both, okay? So we use p of y to the p to the y 1 minus p to the n minus y over the probability of y, or t of x equals y, and that's going to be n choose y, p to the y 1 minus p to the n minus y. Okay? And this is equal to, it's going to be 1 over n choose y. Everything else cancels out. This cancels out, and this cancels out. So it's going to be 1 over that if the sum of xi is equal to y, and it's going to be 0 otherwise. Okay? And this does not, this distribution does not depend on our theta, which is p. Therefore, by the alternate definition of a sufficient statistics, y equals the sum of xi is a sufficient statistic for p. Okay. Note, p of x equals little x and, or given, given t of x equals little y is the probability of selecting a particular arrangement of x equals x1 up to xn, given that there are y1s and n minus y zeros. So we're just saying that it's a particular arrangement. So this probability does not depend on p, and that makes sense to us. We're just trying to find this combination, if you will, of x sub 1, x sub 2. So they're all zeros and ones. let's say. And it doesn't matter, the order of them doesn't matter. It's just we want to choose y1s and n minus y0s, because as long as we have the same number of zeros and the same number of 1s, then y equals sum of xi is going to be the same. It doesn't matter the order in which they were chosen. So this is how many ways can we choose out of n possibilities, how many ways can we choose y1s? That's what this combination is. N objects choose y of a certain category, and that category in this case is 1s. Okay? So that makes intuitive sense for us. Okay, so we're going to stop here for this. So we're going to stop here for this video. Please make sure that you update your notes. If you have questions, please come to virtual office hours. If you need help before virtual office hours, by all means email me, but please send me a picture of the problem, because I may not have it available, and a picture of your work so far, so that I can see how you're approaching it, and that will help me help you. And I will get back to you as soon as it's possible for me to do so. Please take care of yourself and stay safe, because we hope to see you next time.